16 of your textbook, bioavailability and bioequivalence. So let's talk a little bit about these two areas for the next few lectures. Chapter 16. So first I want to read some definitions. These definitions are at the end of the chapter in chapter 16. So in chapter 16, at the end of the chapter, there is a glossary of some terms that pertain to bioavailability and bioequivalence. Please memorize those definitions. I just put it like that. At the end of chapter 16. At the end, but I'm going to give you 3 of those definitions right now because we kind of need them in order to make some sense of today's discussion. Okay. But there are some other definitions like therapeutic equivalence and generic substitution and all that kind of stuff that pertains to bioavailability and bioequivalence. So there at the end of chapter 16, review those. Yes?
No, it's okay. No.
Unless you wanted to. Okay, so bioavailability. Bioavailability. Now here, review these definitions in chapter 16. Bioavailability. Okay, so the definition that we'll use for bioavailability is a measurement that indicates the rate and extent of therapeutically active drug that reaches the systemic or the general circulation. I'll repeat that. A measurement that indicates the rate and extent of therapeutically active drug which reaches the general circulation or the systemic circulation. So it says a measurement of the rate. We talked about rate before. That's how fast it's getting into the bloodstream. And it's also a measurement of the extent of therapeutically active drug. The extent has to do with how much. So when we talk about bioavailability, we're talking about how fast and how much drug actually reaches the systemic circulation. Okay. Bioavailability. And then we have another definition that we might be talking about today, but we'll certainly be talking about it over the next several lectures. Pharmaceutic equivalence. Again, for those that are here, but ain't here, okay, again, these definitions are at the end of chapter 16, okay, but there's some additional definitions that I want you to know. So make sure you know them. So pharmaceutical equivalents are drug products that contain the same amount of the active drug ingredient. Drug products that contain the same amount of the active drug ingredients, but contain different amounts of the inactive ingredients. So you know that in an aspirin tablet, you have more than just acetylsalicylic acid. You got binders and fillers and coloring agents and a host of other excipients in tablets and capsules, whatever. So pharmaceutical equivalents are drug products that contain the same amount of the active drug. Okay. If we were talking about an aspirin tablet, that active component would be the acetylsalicylic acid. Okay. So if you got Felder's brand of aspirin and Bayer's brand of aspirin, 5-gram tablet, if they're going to be pharmaceutical equivalent, they have to have the same amount of aspirin in each one of those tablets. But they can have different amounts of fillers, coloring agents, and all that kind of stuff. All right. If they're pharmaceutical equivalents, they have to be identical in strength and purity and quality. So I'll repeat the whole thing again. Pharmaceutical equivalents are drug products. Notice I'm not saying drugs, I'm saying drug products. Usually we don't dispense, we don't take pure drugs, we take drug products. That's what you talk about in dosage formulations. So drug products that contain the same amount of the active drug ingredient, but contain different amounts of inactive ingredients. Okay. Pharmaceutical equivalents, they must be identical in strength, purity, and quality. So if one tablet has 5 grains of aspirin and the other one has 4 grains of aspirin, they're not pharmaceutical equivalents because they're not identical in strength. Then we have this bioequivalent drug products. Bioequivalent drug products. So, bioequivalent drug products are pharmaceutical equivalents. So usually when we're talking about bioequivalent drug products, first of all, they're usually going to be pharmaceutical equivalents. So bioequivalent drug products are pharmaceutical equivalents which are not significantly different with respect to the rate and extent of absorption when administered at the same dose. I'll repeat that again. And I'll try to, as my colleague said, break it on down. So first of all, for the bioequivalent drug products, we're talking about pharmaceutical equivalents. So we know what pharmaceutical equivalents are, okay? So bioequivalent drug products are pharmaceutical equivalents which are not significantly different. In other words, they pretty much have the same rate and extent of absorption. So basically what we're saying is the biopharmaceutical equivalents are pharmaceutical equivalents that have pretty much the same bioavailability, because we define bioavailability as the measurement of the rate and extent of absorption. So bioequivalent drug products would be pharmaceutical equivalents with no significant difference in their bioavailability. Okay? Because we said that they're not significantly different with respect to the rate and extent of absorption. Rate and extent of absorption is basically bioavailability again. Okay? And they have to be administered at pretty much the same dose. If we're comparing 2 drug products to see if they're bioequivalent or not, we don't want to give one as 10 milligrams and give the other one as 100 milligrams, because there can be some changes in the pharmacokinetics. And we'll talk about that later on in the semester when we talk about dose-dependent pharmacokinetics. Okay? So if we give them at different doses, it's a chance that it could affect the pharmacokinetics, which could alter our conclusions concerning bioavailability and bioequivalence. Okay? So if we're comparing drug products to see if they're pharmaceutical equivalents or bioequivalents, okay, we want to make sure we get the same dose of the drug products. Okay? Questions? We okay? Now, one caveat here, I have in my notes that some drug products may be considered, and this is explained in the textbook better than I can explain it, but sometimes a drug product could be, 2 drug products could be considered as bioequivalent, even if they have different rates of absorption. Not different extent. They're going to be at bioequivalent. They always have to have the same extent of absorption. In other words, the amount of drug that's reaching the bloodstream has to be the same for these 2 drug products. But sometimes 2 drug products can still be considered bioequivalent if they have a difference in the rate of absorption. This is unusual, but it can happen. Sometimes a drug, like with your sustained release preparation or controlled release preparation, of course, if it's a controlled release or sustained release preparation, the rate of absorption is probably going to be different than in a conventional drug product. Okay? But if that difference in the rate of absorption is built into that drug product by design, and if that difference in the rate of absorption is not of any clinical significance, in other words, it doesn't affect the clinical or the therapeutic outcome, okay, then 2 drug products, even if they have differences in the rate, they still could be considered as bioequivalent. They have to have the same extent of absorption, but they can be different in the rate if that rate difference, like I say, is put there by the drug manufacturer by design, such as a controlled release formulation or sustained release formulation. And if that difference in the rate of absorption is not of any clinical or therapeutic significance. So I'm throwing around some terms, but we've already talked about rates of absorption or whatever, when we talked about the absorption model. Okay? I present that absorption model first because there's some things that we're going to be doing as we cover bioavailability and bioequivalence that you're going to have to be competent and have mastered that absorption model. Okay? And some of the following assignments, they're basically gonna be asking you to do some of the same things you've already learned how to do, like calculate the first order absorption rate constant, whatever the case may be. Because that is related to bioavailability, the rate constant and the rates of absorption and that kind of stuff. So some of the problems in chapter 16 are problems that could have been very well placed in the chapter on the absorption model. Okay? All right, so those are some of the definitions. There are two types of bioavailability that I want us to be familiar with. One is relative bioavailability, which I'm going to talk about right now. Relative bioavailability. Relative bioavailability. Okay. And the other one is absolute bioavailability. I'm just not putting it up here, but I'm going to talk about that for the other. So there are two types, relative bioavailability and absolute bioavailability. Relative bioavailability is defined as the availability or the bioavailability of a drug product. In my notes, I just say the availability. Sometimes when we talk about, when you read in the literature, whatever the case may be, and you see the term drug availability, then you're talking about bioavailability, okay? So relative bioavailability is the availability of a drug product as compared to a recognized standard. Relative bioavailability is the availability of a drug product. When I say availability, now I'm not talking about over the counter or you selling the drug product, I'm talking about the actual absorption into the bloodstream, okay? Okay. So you might think of it as the absorption of a drug product compared to a recognized standard. So when I say availability, I'm talking about drug absorption. So relative bioavailability is the availability or the absorption of a drug product as compared to a recognized standard. Okay. So we can calculate relative bioavailability. I'm just going to abbreviate it as RB. Okay. So the relative bioavailability is the area under the curve from 0 to infinity, okay, for drug product A. Now remember, let me say this. For the next, this lecture and maybe a couple of lectures next week, you're going to be hearing me saying the drug products. So when we're talking about bioavailability and bioequivalence, we're not comparing different drugs. We're looking at things like pharmaceutical equivalents, which we said would have to have the drug products that have the same drug, okay, but maybe different inactive ingredients. Okay, so when we're talking about relative bioavailability, we're not going to be comparing aspirin to Tylenol. We're talking about comparing drug products that both of them, or all of them that's being tested have aspirin, or all of them that's being tested have acetaminophen in them. Okay. So we're not comparing different drugs, we're comparing different drug products, different dosage formulations of the drug. Okay, does that make sense? Okay, so keep that in mind. So sometimes you might hear me say, a drug, but we know that we don't normally dispense drugs, we dispense drug products. We don't normally ingest drugs, the pure drug, we ingest the drug product. Okay? So that's what we're looking at. So bioavailability, the area of the curve from 0 to infinity for drug product A. When I say A, that's just a generic term, okay, for one of the drug products, okay? Over the dose administered for drug product A. Divided by the area under the curve from 0 to infinity for drug product B, divided by the dose administered for drug product B. Drug product A, let me see if I can make this. Drug product A is the drug product that's being tested. Remember we said that the relative bioavailability is the availability of the drug product compared to the recognized standard. So the drug product A is the product that's being tested. Let's just say if it was aspirin, for instance. And I had developed a new form of aspirin in my laboratory. Let's just call it Felder's brand, Felder's aspirin. Well, Felder's aspirin, nobody heard of Felder's aspirin before, so Felder's aspirin, we might wanna know what's the relative bioavailability of Felder's aspirin, okay? So that would be the information contained in this numerator. The area under the curve for A would be the test product. That's what's being tested, in this case, Felder's aspirin. This is the dose of Felder's aspirin. And remember, in the definition, I said the availability of a drug product compared to a recognized standard. Okay. Drug product B would be the recognized standard. So drug product B might be Baer's aspirin. We want our standard to be something that's widely used and accepted, you know, in the healthcare field, in the medical field, okay? So we don't want our standard drug product B to be some obscure product that nobody's heard of. Okay? So our drug product B is gonna be the reference standard. So when I publish this information, publish this data in the literature, everybody that reads is gonna recognize, hey, I'm comparing Felder's brand, which I don't know anything about. The reader doesn't know anything about, but they know about Baer aspirin. We don't wanna put something out here in the denominator that nobody's ever heard of before. Does that make sense? So and I'll talk more about the reference standard later on when we talk about the design of bioavailability studies, but drug product B is the reference standard, drug product A is the test product. Now this area under the curve is what we've been learning how to calculate, and that's one of the reasons I haven't had you do areas under the curve on the exam, and when we talk about them, or whatever the case would be. So that's the area under the plasma concentration time curve. For test product A, the area under the plasma concentration time curve for drug product B. Okay, so we had a little bit of experience with calculating areas under the curve. And the equation is adjusted for the dose, okay? Because we already know that if I give a bigger dose of drug product A than drug product B, everything else being equal, then I'm gonna have a bigger area in the curve, okay? So the area in the curve is proportional to the dose. So the dose in this equation kind of corrects for any differences if I administer a different dose of A and B. Now if I administer the same dose of drug product A in the reference, and I hope you can see that this is gonna be the area in the curve for drug product A versus the area in the curve for drug product B, if the doses are the same. Okay? Questions? Talk to them. Yes. Can I do what? Okay. You want me to repeat everything again for the last 5 minutes? Is it funny?
No, he just wants to know what
It's not funny, but you say, can I repeat what I said again? I just said that test product A, you got that?
Yes, sir. Yeah.
The dose of A.
That's further steps.
Huh?
Further product, right?
Yeah. Is that all you want to repeat?
No, I got you.
Okay, see me after class now. Okay, so you can see me right after class. The reference standard, when available, is oftentimes, this recognized reference standard is oftentimes a solution of the pure drug. Now some drug products, we're not gonna even have a solution, like aspirin. I don't think there's an aspirin solution, is there? Y'all don't know this. I don't think it, look, why? I don't think there's an aspirin solution. Why? Why am I thinking that? I'm talking about an aqueous solution of aspirin. Come on, you know this from med chemicals. At least you should. Pharmaceutical chemicals. Is aspirin stable in aqueous environments? Is aspirin stable in water?
It's more like.
Y'all ever heard this before? Is aspirin, would I expect a solution, an aqueous solution of aspirin to be stable?
No.
Why not? What happens? Yeah, I'll talk about it maybe. But at this point, as a P2 student, I would think you ought to cover that somewhere. Aspirin is not stable in an aqueous environment because it's hydrolyzed, okay, it's hydrolyzed, and when it's hydrolyzed, you get this acetic acid, and I forgot the other product, but it's a vinegary smell, you know, as a result of the hydrolysis of aspirin. I think aspirin has, I think it has an ester bond in it also. It has acetylsalicylic, it has a carboxyl group on it. But I think it has an ester bond, it's hydrolyzed acetic acid, and your homework assignment is to tell me the other product But acetic acid smells like vinegar, so if aspirin is like in old fashioned homes, I don't know about today, but in old fashioned homes, a lot of times they had medicine cabinets in the bathroom where the showers were, and folks would be cautioned, you know, don't leave your aspirin, at least if you're gonna have it in the bathroom, in the shower going, whatever, if you get a lot of humidity and stuff like that, make sure that it's, you know, tightly closed. But the best thing is not even have it in the medicine cabinet in the bathroom, because the aspirin will degrade fairly rapidly in aqueous condition. I don't think there's an aqueous preparation of aspirin. I said all of that to say that even though we oftentimes would like for that reference standard to be a solution, why? Forget the aspirin for a moment. Why would we want the reference standard to be a solution if it's available? Come on, think about what we talked about. Physical chemical factors related to absorption, physiological factors. What is it about a solution that's kind of nice? The solution is a dosage form that we would expect is going to have the optimal absorption. So it would be nice to have a reference. It's not always a solution, you know, but it would be nice to have a solution and not make it a suspension, but that's where you're going to have the optimal absorption. So it would be highly unlikely if I had a solution here that this ratio, this relative bioavailability, is probably not going to ever be greater than 100%. I'm saying if I got a solution down here. Because what's going to outperform a solution in terms of absorption? Nothing. So the biggest value that this relative bioavailability can have would be 100%. If the relative bioavailability was 100%, that means that drug product A and drug product B are being absorbed to the same extent. Y'all not talking to me. If it was 100%, this ratio would be equal to 1, right? So when you read in the literature in your textbook that the relative bioavailability of a drug product is 100%, that would just mean that whatever drug product you're talking about, compared to some reference standard, that they absorb, the availability is the same for the both of them. If this value is equal to 50%, that means that the product being tested is only absorbed 50% of the test product, or whatever. That's useful information. Because if I know the relative bioavailability is 50%, then let's say this Felder's brand is a generic brand, but the patient can't afford the Bears aspirin anymore. So this relative bioavailability is 50%. Well, instead of that patient taking 1 tablet every 4 hours, every 6 hours, that patient will have to take 2 tablets in order to get similar plasma concentration. If the availability of this test product was only 50% of what the patient had been taking. Okay? So relative bioavailability is important. So this value can range anywhere from 0 to 1, but when we convert it to percentages, that's 0% to 100%. Okay? Let me say that again, because that wasn't right what I just said. This value can actually exceed 100%. If that test product, if that product is being tested, if it outperforms my reference standard, this ratio will be bigger than 1 would. If my test aspirin kicks the butt of their aspirin, this is going to be a bigger ratio than number 1, right? So relative bioavailability can exceed 100%. But now if we got a solution down here, the reference standard is highly unlikely that it's going to ever go above 100%. Does that make sense? Seriously?
Yeah.
But relative bioavailability can exceed 100%, depending on the reference standard. We can also calculate relative bioavailability using urinary excretion data, and that's just equal to the AU infinity value for drug product A. AU infinity now is the cumulative amount of drugs excreted in the urine, okay, over the dose of drug product A. And that's all divided by the AU infinity value for drug product B. B again is the reference standard divided upon the dose of A, divided by the dose of B, the dose of drug product B, which is the reference standard. This is urinary excretion data. This is we're looking at plasma concentrations. This is the area under the plasma concentration time curve. Here, this is AU infinity. This is the cumulative amount of drug excreted in the urine for drug product A. In the denominator, we have the cumulative amount of drug excreted in the urine for drug product B divided by the dose of B. Okay? So plasma data, urinary excretion data. Why we want to do urinary excretion data? Well, we might not have a convenient way of measuring concentrations in the plasma so that we can get area under the curve. Remember we said before that sometimes drug concentrated in the urine because that drug goes through the glomerulus and into the glomerular filtrate. A lot of that is water. Yeah, drug is in that water, but as it goes around the proximal tubule and the mucopinally and the distal tubule, and all three of those sections of the nephron, the kidney, okay, that water, most of that water gets reabsorbed. Because if we were losing that water that's being filtered at the glomerulus, we would die a quick and ugly death of thirst. So the body reabsorbs most of that water that's filtered at the glomerulus, okay? So sometimes it's easier to measure drugs in the urine, okay, because if that drug, remember the calculations you talked about dilution and concentration. So if that drug is in the glomerular filtrate and it's filtered at the glomerulus, but it's in the solvent, water, I'm just calling it water, it's mostly water, okay? And if that water gets reabsorbed, what's that gonna tend to do? It's gonna concentrate the drug, right? So a lot of times it's easier to see the drug in the urine than it is in the plasma, okay, because of that concentration effect in the urine. So there's two different ways we can measure relative bioavailability. Two common ways at least of measuring. Again, this can exceed 100%, but normally it's going to be somewhere between 0 and 100%. But again, if that test product, if the test product A, if it outperforms the reference standard, then this ratio will be bigger than 100%. Okay? All right, very good. The next type of bioavailability that I want. Any questions here? Yes, ma'am.
Do we represent as a percentage?
Say that again.
Do we represent relative bioavailability as a percentage that we can calculate from?
Can we do what with that? I'm not understanding you.
Does it come out to a percentage?
Yes. Usually when you read about bioavailability, you don't see it expressed in percentage, okay? But I'm just giving you, so this ratio divided times 100 would be the percentage. This ratio times 100 would be the percentage. So if this ratio is equal to 0.5, that would be 50% relative bioavailability. If it was equal to 0.7, that would be 70% of bio. That's a good question, okay? Because I'm just tossing around percentages or whatever. But really, these are fractional values, decimal numbers. So when you read about bioavailability, whether it's relative or absolute, okay? If something has a relative bioavailability of 80%, this ratio is equal to 0.8. So to convert it to a percentage, which is the way it's normally presented when we're given a seminar or in a textbook when you read it, it'll be in terms of percentage. But that's a good question. I want you to recognize it came from these relationships, okay? Now, when we do calculations with relative and absolute bioavailability, we don't use a huge percentage. We use just this decimal number in the calculations, okay? All right, so the other type of bioavailability that I want to talk about right quick is absolute bioavailability. This is the second one, absolute. And let me give you a definition. So absolute bioavailability is a measurement of the availability of the drug compared to an IV dose of the drug, relative to an IV dose of the drug. So absolute bioavailability is the absorption of the drug product or the availability of the drug product as compared to an IV dose of the drug. So when I write the equation on the board, maybe the definition So I just call absolute bioavailability AB. And that's equal to the area under the curve from 0 to infinity for a PO dose, an oral dose, divided by the dose administered orally, all over the area under the curve from 0 to infinity after an IV dose, divided by the dose administered IV. So, with absolute bioavailability, this area in the curve now is the area of the plasma concentration time curve after an oral dose of the drug. We have to adjust for the dose, okay, because especially now with absolute bioavailability, a lot of times we have to give a smaller dose IV, because if we give the drug IV, a lot of times, most of the time we're putting it, not most of the time, all the time, we're putting it right into the veins. So a lot of times we do have to adjust the dose for an IV. It's usually going to be oftentimes be a smaller dose. So we need that in the equation. But in a situation just like with relative bioavailability, if the oral dose and the IV dose, if they're the same, then it's just putting the collapses to area in the curve PO divided by area in the curve IV. If the dose is the dosage value will cancel out. With absolute bioavailability, you are more likely to have a difference in the oral dose versus the IV dose. Okay? Because the IV dose, again, is right into the bloodstream, so you don't want to have toxic effects. So, absolute bioavailability. With regard to the question that Linda asked, okay, again, this is a decimal number or fractional value as it is. Okay, so the absolute bioavailability was 70%. That means this ratio right here would equal to 0.7 for the absolute bioavailability to be expressed as 70%. So if the absolute bioavailability was 50%, that means this ratio is equal to 0.5. If I want to convert percentage and I multiply the 0.5 times 100, that would be 50%. Is that clear? Same thing we did with relative bioavailability. Now a couple of contrast and comparison. Okay? One is that this joker here cannot exceed 100% under any circumstances. Ain't no way on God's green earth this PO dose is going to trump an IV dose. So this ain't gonna never go above 100%. I mean, outside of experimental error, if you're reading a study and they said the absolute bioavailability was 101 plus or minus 2%, then you just have to interpret that as 100%. You know what I'm saying? Because you can have experimental error, so it might say 101 plus or minus 2% or 3% or whatever. But you read that as 100%, okay? But you know from your biostatistics course, you can have experimental error, because these studies for absolute bioavailability and relative bioavailability, usually they're done in tens or dozens of people. We don't determine that the absolute bioavailability of a drug product is 80% just based on a study of one person. Does that make sense? I mean, drug studies, they use a whole lot. So you're gonna have, standard deviations and all that kind of stuff. But from a practical point of view, okay, this joke here ain't gonna go above 100%. Ain't nothing gonna trump that IV dose. Nothing. So the highest value you can expect or ever have absolute bioavailability is 100%, or this ratio would be equal to 1. Okay? That's the highest value. If the absolute bioavailability was 50%, just so you can understand what's going on. If the absolute bioavailability, let's say the dose administered for the PO dose was equal to 500 milligrams of some drug, and the dose for the IV was equal to, we're gonna just make it the same, just so we can make the concept clear. So I get the same dose, PO and IV. So now the dose is gonna cancel out, and the absolute bioavailability that I found was equal to 0.5. In other words, if, so in your notes or whatever, your recording, whatever, I'm just pulling this 0.5 out of the sky. I could say 0.6, and I don't want you to go back later on this evening or whenever you're finished saying, where that 0.5? I'm just pulling it out of the sky. So I'm saying if. Okay. That's a big if, okay. Then that means of this 500 milligram dose, only 250 milligrams reach the bloodstream. That's what it means. Only 250 milligrams actually got absorbed in that absorption model that we were dealing with for the last few months lectures. Remember the F times G, with the error and the Ka and stuff like that? Okay. If the dose was 500 milligrams, and I did an absolute bioavailability study, area to occur after the oral dose, area to occur after the IV dose, and I looked at that ratio, and that ratio came out to 0.5, that would tell me that only 50% of that oral dose is reaching the bloodstream. That's why it's called absolute. It's called absolute. It ain't relative, because relative bioavailability, depending on what my reference standard is, if I say relative bioavailability is 100%, look at whatever you wrote down, whatever you recorded. If I say the relative bioavailability is 100%, does that mean that that reference product was 100% absorbed? If relative bioavailability is 100%, does that mean that the reference product is 100% absorbed? No, it doesn't. It just means it's absorbed to the same extent as your reference standard. It just means it's absorbed to, the reference standard may not have been absorbed 100% itself. Right? The reference standard in the relative bioavailability study may not have been absorbed 100% itself. So 100% relative bioavailability just means that the test product and the reference standard are absorbed to the same extent. Does that make sense? Absolute bioavailability, that's what it's called absolute for a reason, because the absolute bioavailability is 50%. That means that PO dose in this equation here, that only 50% of it is bloodstream. That's it. If that absolute bioavailability was 80%, that means that only, if it was 80%, that means only 400 milligrams of that 500 milligram dose actually ended up reaching the bloodstream. 400 milligrams, yeah, 0.8 times 500 is 400. Questions? This absolute bioavailability is the same as F in that fancy equation for concentration after an overdose. The fraction of the dose absorbed, for our purposes, we consider that the same as absolute bioavailability. Remember I told you I'm going to teach you how to calculate F? Here it is right here. Here it is right here. It's a fraction of the dose that gets absorbed. So 0.5, if it's 0.5, that means that the fraction of the dose that got absorbed was 0.5, or 50%. It's that F in the equation. So if you're doing a calculation, and I have done this on tests sometimes, you probably won't see it on this exam, but we're not going to have bioavailability on this exam. But it's just so amazing, you know, on tests sometimes, you know, we get the bioavailability stuff on tests. Okay, I have to calculate the absolute bioavailability. Okay, they got errors in the curve, and they calculate the absolute bioavailability. And then I ask them to calculate the concentration of drug in the blood after a certain dose. So you know they got Ka and they got KEL. You know if you need this stuff, you know they know the dose. Okay, they know the volume of distribution. The kind of stuff that we need to calculate the plasma concentration. Now I'm telling you this because I don't want it to happen to you, but like I said, it's going to happen to somebody in here, but it doesn't have to be you. So now I go to my students and say, calculate the concentration. They've already calculated the absolute bioavailability to 0.5. So I say calculate the concentration at 3 hours after the dose. So they need to use this equation right here, F times G times Ka. What we worked on in the lab this week, Ka, and last week. Okay. Times e to the power negative KEL times T, e to the power negative Ka times T. So now they have all this information, and I say, tell me how much, calculate the concentration of drug in the blood at 3 hours. You would not believe how many hands were doing the test. Dr. Phillips, don't we need help? I'm testing for understanding. Don't we need help? But in the previous part, you've already calculated the absolute bioavailability. So just like I'm telling you, I told every class in the past too, but now come test time, whatever, you know, I'm asking them to calculate the concentration at a given time. They say, well, don't we need F? My response is, I don't know. So don't you fall into that, you know, I'm telling you that this absolute bioavailability is there. Okay. That is F, so if you calculated F to be 0.8, that's what you would put right here in this equation. Trying to connect the dots. You calculated F to be 0.9 from this equation, then you put 0.9 right here in this equation. Questions? Okay, and so we've already said absolute bioavailability, it cannot exceed 100%. The lowest value you can have absolute bioavailability is 0. If it's 0%, that means ain't none of the dose given sold. If absolute bioavailability is 0. We do have some situations where, some drugs are not given as an oral dose because, they're not absorbed for it. The other thing I want to point out here in this equation, which is even though here on the board I say PO, oral, and that's what I have in my notes, don't think absolute bioavailability just pertains to an oral dose. Let's say if the drug product was designed for intramuscular administration. So if it's designed for intramuscular administration, it's going to have to be absorbed, right? Okay. So instead of area under the curve after an oral dose, we would have area under the curve IM for the intramuscular dose. So this is just a general form of the equation. Whatever the dosage form is what's going to be in the numerator. So I'm saying PO. If you look at this equation as written, it just assumes that absolute bioavailability only pertains to oral dosage. I'm saying no. If it was a suppository, and I wanted to like theophylline and some other drugs, you have suppositories. In order for that theophylline to be effective as a suppository, it has to be absorbed from the region of the rectum into the bloodstream to exert its effect, right? So this would be the area of the curve after the, I don't know what you call it, is that intrarectal or whatever? Intrarectal, I don't know if that's a right term or not. But whatever that suppository form of the administration is, that's what this, it wouldn't be PO. Okay? You're not gonna give suppository orally, that's my point. So don't think that this only applies to just oral dose. The absolute bioavailability can be calculated for any route of administration where absorption occurs. It's just that we know that the oral route of administration is the most common route, so that's why I wrote PO. Are we okay with that? Okay. The only other thing I'm gonna say, and I'm gonna end this discussion, I have to try to answer any questions, that plasma concentration, the area in the curve, this is the area in the plasma concentration time curve. Just like with relative bioavailability, we can also calculate absolute bioavailability using urinary excretion data. And we just look at AU infinity after the oral dose or the route of administration that requires absorption divided by the dose PO over AU infinity for the IV dose divided by the dose administered IV. And I apologize for writing downhill. Okay. I'm writing like I'm left-handed now. So this is absolute bioavailability is equal to AU infinity after the oral dose divided by the oral dose administered over area under the curve, not area under the curve, AU infinity. Drug in the urine. Cumulative amount of drug in the urine after the IV dose divided by the dose IV. So this can be used to calculate, this equation can be used to calculate absolute bioavailability after an oral dose and an IV dose is given. Now, the other thing I didn't say, I just thought about this. Make a note in your relative bioavailability and absolute bioavailability. Now, we're not giving, in the case of absolute bioavailability, we're not giving the oral dose and the IV dose at the same time. And that's something I didn't think to say, and it seemed like it should be obvious. It is to me, but maybe not to you. So we give the oral dose, we have to wait for, 5 half-lives alone for all of that drug to get out of the body. And then we follow up, at a later time with the IV dose. Or we get an IV dose first, we have to wait for 5 more half-lives for all the drugs to be eliminated. Because if we give these drugs concurrently, we ain't gonna know when we're looking at area of the curve and concentration, we ain't gonna know the concentration we're looking at depends on oral dose or the IV dose. But we wanna make sure that when we give a dose, that we allow a washout period. Washout is usually the elimination period. So the concentration we're looking at, we'll know that they came from this, or this, because it's the same drug in both of them. Because we need to determine what this FA rate is. How we gonna calculate concentration, estimate concentration, if we don't know how much drug is in the bloodstream? How we gonna know that when this patient was in the hospital, taking a parenteral form of theophylline, maybe IV, maybe intramuscular, whatever. Now this patient is gonna be discharged, and we wanna switch that patient over to theophylline tablets or capsules. How are we gonna know what dose of theophylline that we're gonna prescribe for that patient if we don't know to what extent the theophylline is exposed? The patient in the hospital might be taking, IV theophylline or intramuscular or some other formulation of theophylline, but now the patient's gonna be discharged in ambulatory rehabilitation. To have that patient taking a parenteral, injecting himself ain't gonna work. So now I need to give this patient some oral form of medication or whatever the case may be. Well, I don't know what that oral form, what effect it's gonna have on blood concentrations, if I can make some predictions, estimations as to what concentration is gonna look like. I would like for the concentrations post-discharge, the patient now is gonna be on theophylline tablets or capsules or whatever. I would like those concentrations post-discharge to look similar to the concentrations that the patient was being managed on when he or she was hospitalized. Does that make sense? But it'd be kind of hard if I don't know, have some idea about, absolute bioavailability and or possibly relative bioavailability of that drug. Okay? So that's kind of the idea. When drug products are being produced by these different drug companies or whatever the case may be, this is one of the first studies they're going to do, because all things being equal, it would be much nicer if I'm Merck or if I'm Pfizer or whoever, if I could reduce that drug product as an oral dosage formulation. Okay, that's where I'm going to get, like you told me the other day, that's where I'm going to get the greatest probability of adherence. Okay? So they have to do these types of studies, relative and absolute bioavailability studies, to even see if this product that they're working on, if it's going to be feasible to make it as an oral formulation. Because if the absolute bioavailability is low, let's say the absolute bioavailability is only 10%. I hope you can see that the lower that absolute bioavailability is, look at this for a moment, brain game, everybody else. The lower this value is right here, the bigger the dose you're going to have to give in order to get a certain concentration. If the therapeutic concentration, let's just say, is 10 milligrams per liter. Okay. As this F value goes down, in order to get to 10, I'm going to have to, assuming that K and the K, all that kind of stuff stays the same. Okay. Then as F goes down, I'll have to give a bigger dose in order to reach a given concentration. If I got to give a bigger dose, you already know what that's going to mean, right?
So if absorption is low, the dose has to.
Yeah, in order to reach a certain concentration, you know the therapeutic effect is based on these concentrations here. So in pharmacokinetics, we focus on all these fancy equations and stuff like that, but ultimate desire is that we effectively and safely treat that patient based on concentration. So I'm glad we're having this discussion too, because you've learned all these fancy equations, but when it's all said and done, we're trying to get therapeutic concentration. So therapeutic concentration is based on these fancy pharmacokinetic equations. So that's all right. Well, I'm going to stop right there, and we'll continue.